And so we approached the process a little bit differently than the first time around. Now we had teams that we all worked together, so we were able to combine design, engineering, and manufacturing process all at the same time. But somewhere along the way, we changed the manufacturing process to be fully automated. And so we leaned into this whole new way of manufacturing a car, but we had already engineered it. So things didn't quite go as well as planned.
It was an amazing product, but it landed us in production hell. Many of us who lived through that carry those battle scars. It was a great idea, but it wasn't the right timing. Like Franz said, automating something that we designed to be built manually is super hard. And we have many, many failed examples of that at the Fremont factory that we ripped out. But some of them eventually still work. This is one I actually worked on with a small team of engineers. It's still running today. And some of the engineers that came by said we couldn't do it are no longer with the company, but it's running, and it's running faster than ever. So we kind of self-imposed constraints on the design when we were doing it to be built manually, and we really didn't think about it.
We knew we had to improve the process further. And with Cybertruck, we designed a vehicle around a vision that actually started with the manufacturing process. And in this case, the materials dictated the design.
Forming full hard stainless steel isn't rocket science, but it sure isn't easy, and it limited the way we could do it. What that stainless steel opportunity did for us, it has let us rethink the factory footprint. We don't stamp those, that's a huge part of it. We don't even paint them. So our footprint got smaller, and we started to think about innovative ways to take those constraints and make great products. After all that, we would design, engineer, manufacture, and plan for automation happening together. It gives us the opportunity to question requirements. This is something that is fundamentally only available at Tesla. In the places I used to work and the top manufacturing companies in the world, they don't sit together.
Yeah,
we are one team.
Nowhere I know has all these teams together thinking about these processes from the very beginning.
In fact, all of those engineering teams, manufacturing, design, automation, they're all in one org. They all report to one person. We can't point fingers at each other, so we have to solve them together, which is the best way to innovate. In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx and more output per unit. Faster, less CapEx, more output per unit dollar. Zach's going to go into more details on this later, but it also means through this innovation and some of what my other engineering colleagues are going to talk to you about in the future, we'll reduce costs as much as 50%. This is the 2-for-1 concept you hear me and Elon talking about on earnings calls.
So since we launched it back in 2017, we've continuously improved that powertrain and the factory that builds it. So the drive unit, the engine of the car, is 20% lighter for the same power. We use 25% less heavy rare earths than when we started. And the powertrain factory, which is behind me today, is 75% smaller and 65% cheaper than the one that we originally built. And what I really want to emphasize is that we did all of this without compromise. Our cars are just as powerful, they go just as far, they cost the same or less, and the factories have the same output. So, how did we do that? We did it by designing the entire vehicle and the entire factory together as one company. And this sets Tesla apart. We have small and highly capable teams, and to make a critical decision, we can have the battery cell chemists, the mechanical engineers, the manufacturing engineers, the supply chain team, the automation designers, the software programmers, all in one room, working together in real time. And that allows us to make decisions that are best for the whole car and to make them really fast. And that approach is unlike traditional automotive engineering, which is really fractured. When you are making a new product, it's not enough to think about the product itself. You have to think about how you're going to make it at scale. So at Tesla, our powertrain and our powertrain manufacturing equipment is both designed under one roof. The engineers who are designing the motor, they are in the same room as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble.
So I'm going to talk briefly about a few things that we've changed over the years since the Model S. With the Model 3, Tesla started designing an increasing share of our controllers by merging controllers together, and we were able to simplify the design with a significant reduction in wire count and weight. Going from S to 3, we reduced the wire harness by 17 kilograms compared to Model S. And this is a pretty big deal, and just to put that into context, our VP of Engineering, Lars, will deliver a bottle of your favorite spirit to your desk if you manage to save a kilogram of weight from the car. So this improvement cost him quite a lot. The original Model 3 controllers were enhanced and then built into Model Y. Those improved controllers were then moved back into Model 3 when we introduced the heat pump. At that point, we had shared controllers across both cars, which helped simplify our supply chain. Those Model 3 and Y controller designs were then updated and enhanced for the new versions of Model S and X that we introduced in 2021. For Cybertruck, we are now designing 85% of the controllers in the car. For the next gen platform, we're going to finish the job and be designing 100% of the controllers to give us full control of the design and the supply chain at the component level. Having full control of the supply chain at the component level has been critical to Tesla over the last few years as the supply constraints have hampered our ability to build cars.
And with that control comes control over all the software, which enables us to develop features and functionality that we never even dreamed of at the time we designed the hardware. So that's why you see software in your cars getting better and better over time in ways that we didn't even think of when we designed the hardware in the first place. Mm-hmm. We've analyzed patterns in the way the fleet drives and charges to optimally size battery packs for our next generations of vehicles. And you'll hear lots of other examples throughout the rest of the day about how we're using data to inform decisions in the product and in manufacturing. So you've heard a lot from Pete, Colin, and others about how important vertical integration is for us in hardware, but it's especially important for us in software. And this is extremely difficult from the way the rest of the traditional automotive supply chain is set up. In most situations, all the controllers in the car are delivered by different Tier 1 suppliers, whose software is written by Tier 2 suppliers, who farm some of that software out to different Tier 3 suppliers, and so on and so on. Making a change that spans multiple components takes months of coordination before any work can even start. And furthermore, integration of software and the server side with what's happening in our vehicles has always been a core part of our DNA and enables us to do things that nobody else can. Most engineers think about the vehicle as a complete, consolidated, fully contained system. But in the software team, we think about the system as including the vehicle as well as all of our back-end server-side applications and infrastructure and the resultant feedback loop from the entire fleet that informs all the decisions we make as an engineering team. Okay, so far you've heard me talk a lot about how we leverage our software systems to iterate quickly on the customer-facing product. But what I haven't talked about, and what we haven't said much about publicly in general, is how we leverage these capabilities in our own internal operations. So for example, in the early days of manufacturing Model S, we very quickly realized that there are a lot of different ways you could misassemble a car. You could forget to plug in a wire, you could not fully set a connector, you could pull a part from the wrong bin. So when we designed our manufacturing processes for Model 3 and all of our other vehicles going forward, we took a page from the software playbook, which says, test early and test often. And we applied that mantra to every single car that we build at every step of the assembly line. So now, when a production associate plugs something into the car, the central car computer sees that connection, confirms that it's the correct part for the type of car that's supposed to be built, installs a software update if necessary, checks configurations and calibrations, and runs a barrage of tests on that thing and all the other things that are connected to it. And if it finds an anomaly that can't be fixed purely with software, it throws an alert immediately that is displayed prominently on the vehicle's display, as well as sent to back-end command and control systems, so that a human can come over and fix the problem before the rest of the car gets built on top of it.
and what really separates us from the typical automotive supply chain. As you've seen in presentations prior from Pete and Drew and some others, Tesla designs a lot of the subcomponents that go into our vehicles. So we're not buying things that are off the shelf from suppliers. So supply chain is not purely a commercial relationship as it is in most other companies. We actually have an arm within supply chain called Supply Industrialization Engineering. And the burden of taking a drawing, a design from concept and turning it into thousands of products produced at the right cost and at the right yield falls with this group. Of course, they work very closely with design engineering. But really, the level of detail that our engineers get involved in terms of building the capability of the suppliers is pretty detailed. So, once we get a new part, naturally, with electric vehicles, a lot of the supply chain doesn't exist. Our engineers would basically take the drawing, turn it into a manufacturing concept, do the equipment selection, and physically go to the supplier and stay there for weeks or months, however long it takes, to basically do the line bring up. Once the line is brought up and we're hitting the right rate, the right quality, at the right yield, then we work on things like automation and yield improvement and those types of activities. So there's a big group of mechanical, electrical, industrial, you name it, engineers within supply chain, and it's their responsibility to take care of this. Now, this is a huge strategic advantage because we manage every detail of our supply chain, because we're so integrated with our partners that we know about issues before they happen. It's almost live. We've got dashboards, we've got connections, and across the 10,000 or so factories across the world that are making our components, we have a pretty good view of the health of those suppliers, and this has been a key asset in how we've been able to kind of manage things through a lot of different issues over the past couple of years. This is an example of one tier 1 part number that's a very complex assembly to manage at the tier 2 level. And there's more than 7,000 components here. There's as we stand here, a component's being assembled onto a car computer every 1.4 milliseconds. The line that builds this computer is the length of a football field. So it's quite complicated. And initially, when we first started building this board, due to the complexity of it, we had to rely heavily on labor. But once we dialed in the quality, the rates, and the yield, we started focusing on making this more efficient. The only way to control cost is by removing labor. The first step is removing labor. The second step is fully automating. The third step is turning off the lights and letting the factory run, ideally. And that's going to be the goal for us here. So 95%, but our work is not done. We're going to be going a lot further than this. So this illustrates the point that a part is not a part. A part has a lot of complexity underneath it. Supply chain is a game of multiple tiers. And what's made us successful is our involvement in all the details with our supply engineers that are Tesla employees. They're Tesla supply engineers. So they're like on our payroll that go and ramp up these capabilities at our suppliers. And then just managing each and every attribute of it. 7,000 a day through the chip shortage, through the pandemic, through all the other stuff that we had to deal with, was very difficult to manage, but because we had all the details, we were able to pull this off.
Now, I would like to talk about a page that we took out of the electronic playbook and applied it to the mechanical side. Our vehicles use currently the heat pump-based technology for the thermal system. But before heat pump, our vehicles used to have a dispersed thermal system connected by hoses. Engineering was inspired from circuit boards. So there are 4 videos playing at the same time. One is the video of the manual line that was created when we started the production. And this manual line produced a lot of quality issues, let alone throughput. So we quickly pivoted to a semi-automated line. But in spite of that, although the throughput was great, the quality issues sustained. So our team decided that fully automated is the only way to go. So before we automate the line, we created a 3D simulation. Now, not many companies or teams have this capability, where at this point, now when a part gets spec'd, we have the ability to create a 3D simulation of all the complex sub-assemblies that would be involved in making the part, and tell the suppliers exactly what equipment to purchase, what to test, and create an end-to-end line in simulation. And that's what we did here. So with the help of the simulation, we had a very detailed sub-assembly cell, which was juxtaposed with the supplier's factory layout. And then we, after a back and forth of iteration and optimizing the processes, we implemented this fully automated line in less than 8 months. And the results were remarkable. 99% reduction in labor force. So in a line that would need 1,000 associates to build the super manifold in full volume now just takes 10 associates. And the quality also went up by an order of magnitude. We have a defect rate of less than 0.005%, and a super manifold rolls out every 7 seconds because we have created many automated lines. And these factories are the size of 2 football fields, by the way.
To build more factories is the start to building more cars, and we're certainly the expert of it. This is the before and after image showing you the progress we made back in 2019 when we built a gigafactory in Shanghai. So in 9.5 months' time, we built a greenfield project to establish the vehicle factory. And 3 months later, we started to deliver our first customer vehicle. People always ask me, how Tesla can build a factory that fast. Really, we learned from our Fremont factory a lot. We talked to the survivor from the production hell and tried to avoid all the mistakes we made. We decided to design a straight line with the minimum number of up and downs and turns for easier manufacturability and easier construction. We also challenged all the assumptions that people ever know to build a vehicle factory. When we delete and simplified all the redundancies and the buffers, that's helped us to save a lot of time.
Rodney Westmoreland, managing the construction here at Tesla. The thing that sets us apart is that we're integrated in the manufacturing process. So every detail that comes from Drew's mouth is directly implicated into the system that we're building. That way, what would typically take 3 or 4 months to create a specification, our design team is working right with the manufacturing team to allow us to speed that process up tremendously. So.
Yeah, it's definitely an important part of the vertically integrated approach is to be able to design the factory around the equipment, in fact, together with the equipment, so that you can build the factory at lower cost and more quickly.
How can we reduce the cycle time, keep improving efficiency? We follow the philosophy Elon shared about building rockets, which is questioning, basically find the right problem to solve, and we start with delete, simplify, then we try to accelerate, pressurize the line, and find if the solution actually work, and at last we think about the automation. Right now, we have an integrated global organization from production all the way to sales and delivery service. This will help us to strengthen feedback loop between manufacturing and the service. We obviously want to bring a delightful customer ownership experience to our car owners. With this direct feedback loop, we be able to turn customer escalations and the feedback into quick actions and improvement on the shop floor immediately. With that effort in the past 6 months, we'll be able to reduce the time in service and early ownership service, also service appointment wait time significantly.
And we've also continued to focus on refining the way we make cells and the factories that the cells go inside. As you can see on this chart, from typical 2170 cylindrical cells to 4680, we made a huge leap, which is basically a 5x reduction in the factory footprint and volume and footprint. And then from going from what we did in Fremont and our pilot line to Texas, we improved further, and we're improving again when we go into Nevada. And what this actually represents is a series of actions taken by a very integrated, holistic design team across the product design, the manufacturing design, the process design, the equipment design, and the facility design. They all need to work together to make this happen. And you can see on the bottom, just as an example of simplicity up, investment down, and scaling up. Parts, we've reduced the number of parts in the cell, the number of processes, significant reduction in the number of processes, and collaborating with those 5 design groups, we've been able to end up with a factory that's 10 times smaller volumetrically, which means it's faster to get built. It's much lower capex per gigawatt hour output, and we can go and scale, to our objectives of, 240 total terawatt hours, 1 terawatt hour a year of stationary storage, and 20 million vehicles a year, with the scalability that is required to achieve our goals. And we're not just looking at the cell factory itself, but also upstream materials where necessary. What you see here is the rendering of the 50 gigawatt hour a year Corpus Christi lithium refinery that we've already broken ground on here in Texas. The facility will start commissioning by the end of 2023, this year. This is a good example of something where we're basically talking about breaking ground and starting commissioning within 10 months, and with actual production within 12 months. That's the target, similar to what we did in Shanghai. Again, the result of collaboration and internal execution of construction.
Second point of how we got here, a relentless focus on speed of execution, and there's 2 points to be made here. First one is in building factories. What you're seeing here is a time lapse of the mega factory that was built in Lathrop. We took it from a JCPenney distribution center to a world-class manufacturing facility in less than 12 months, which is incredible. And really, the way that we did this is similar to what my colleagues have described. It's leveraging the vertical integration of Tesla. It's getting the vehicle manufacturing team in the same room as construction and engineering and making decisions quickly with all the stakeholders and decision makers. We're using the lessons learned from Lathrop as we speak, as we plan for our next factories.
People want to join our mission, and we need to grow, and we need to hire the best people. Engineers want to work for Tesla. Look at number 1 and number 2, SpaceX and Tesla. In 2021, we got 3 million applicants. 3 million, that's incredible. And our culture at Tesla is anyone at any time can raise an idea or make an improvement suggestion across safety, people, cost, production, quality. Because we have a very simple process called take charge. And take charge is really employee engagement. And as take charges go up, as you can see in this graph, injuries go down. And you know why? People who do the work, the people who do the work know how to improve the work.
If we go back a little bit in time, and we talk about when we launched Model 3 in the Fremont factory, we went from 2,000 cars per week, which was S and X, adding 5,000 a week to that for Model 3 got us to 7,000 cars a week. You've heard some folks here today talk about production hell. What I don't think we've ever talked about as a company is back office operations hell, which also happened at the same time. And 7,000 cars a week, 350,000 cars a year, we want to go to 20 million cars a year, and we're struggling at 7,000. And we're saying to ourselves, we have to completely rethink the way that we're managing our back office operations if we have any hope of efficiently scaling this company. And so this began a process that we're still continuing to work on today, but it's something that we refer to as the Tesla operating system. So in the same way that we're vertically integrated into the software that manages our cars, we've also vertically integrated into the software that runs our company. And all of our major departments in the company are using, not all of them yet, but almost all of them are using our in-house software. Most recently, we removed third-party recruiting software, and we're now running our own recruiting software as a company. And this matters a lot because rather than having a complex web of third-party systems that are generic solutions that take a lot of effort to customize for our particular needs, we've been able to put in place with an in-house applications engineering team dedicated, lightweight software that does only what we need it to do and nothing more. And that team works very closely with process improvement teams that sit within the business, who are looking through all of the processes that we're managing as a company and following the exact same process that Tom mentioned in the manufacturing space to look at our processes, delete process steps that we don't need, simplify process steps that are existing, and automate what's remaining. And the results of this have been quite staggering, to be frank. I think it's exceeded our expectations as well. On the left side of this chart are some examples of the efficiency improvements that we've seen within our SG&A areas as a result of this strategy. The North American sales team is 4 times more efficient now than they were in 2018. Order operations team, financial services, I mean, these levels of improvement are large, and there's not enough pixels on the slide here to list out everything, so it's just a couple of examples.
We're going to address whatever we think the limiting factor is at any point in time. So we would like to do the least amount possible. So we don't want to get into the mining or refining sector. We will do that if we have to.
We do have large suppliers of lithium right now, and they are aware of how we're approaching the Corpus refinery and the technologies we're trying there. And the reason we're making them aware of it is because we think they're fundamentally more scalable. And as we prove them out, we plan to share that with them. Because as Elon says, it's not really like we want to do these things. We're doing them because it's not happening fast enough. So if we can prove that it can be done faster, the intention is to transfer that knowledge to our current suppliers. And the same is actually true. It was actually a clay process that we're playing with and we continue to work on. Same is true on that. So we've worked with our suppliers as well on trials, and we're sharing knowledge there. And the intention is just to help the whole world do this better. You can't improve something you don't measure, and we're like ruthless measurers at Tesla. And once you start measuring things that contribute to operational efficiency, you actually have a path to doing something about it. So I guess the key is a good measuring stick. And we have clear end goals. And we are, every week that goes by, making progress towards those end goals, whether it's speed of the tool, yield of that process, or the downstream process. The great thing about where we are with the overcapacity that Elon mentioned is it's giving us the opportunity to experiment as we go, rather than just being stuck to something that we happened to kick off a year and a half ago and it is here. Something that Elon has said to the team many times is it's okay to scrap equipment or money. It's not okay to scrap time. So the way we've been approaching it is probabilistically, what do we think is the most likely thing to succeed? And even actually in the factory here, you saw more than one anode line. They are actually operating 2 slightly different versions of the final process step of the powder entering the tool. And it's a competition, which is going to be higher yield, which is going to perform better. And we have the luxury to be able to do that. And we're taking full advantage of it to advance the technology as quickly as possible.